Thank you for joining us on this webinar on CPU250 I O configuration using variables. We'll go with the standard run of things. The presentation's about 20 minutes, but if you've any questions, put them in at any point and we'll get to them at the end.
Hello and welcome to today's webinar. Today we will look at CPU250 I O configuration using variables. Let us take a look at our agenda for today. We are going to start with a quick review of the CPU250 and then we will go straight into our topic. Why would we use variables for configuration? That is the first question we are going to answer. And then we're going to talk about some of the I/O adjustments that we can make at runtime. And there will be demonstrations throughout, and we will finish with a Q&A session. The new micro-modular controllers are the CPU200 and the CPU250. They are part of the Micro series, which is our entry-level product line for simple and smart applications. There is a whole lot of applications you can solve with the Micro series. That now includes the CPU200, which is on the right at the bottom. With no built-in I/O, you can add I/O strictly on the side using OCS I/O modules. And then in the upper right, we have our CPU250, which does feature built-in I/O, but you can also add additional I/O using OCS I/O modules. We have been focusing a lot on the CPU250 for a good reason. It has lots of great connectivity with Ethernet and serial ports, and CAN ports, supports all those great protocols that you see in the lower left, has all kinds of capabilities including, as we have already mentioned, the ability to add OCS I/O modules on the side directly to add additional I/O. The built-in I/O for the CPU250 has got a total of 34 built-in I/O points, 8 of which are what we call flexible inputs. They can be digital or analog, and we also feature 8 analog outs, which is a large number of analog outputs for a product in this product category. And today we are focusing, as we have mentioned already, how do you do some I/O configuration with variables, so you can make some runtime adjustments of your I/O configuration without having the use of Cscape. Now let's talk about configuration. Typically with PLCs and other control type devices like a Horner OCS or Horner modular controller, how does that typically work? Well, traditionally, you would use your application development software program and you would configure your I/O. As you develop your machine and after you deploy your machine, you would not make any configuration changes at all. And typically, that works just fine, but there are some scenarios where it is useful to make adjustments without bringing your programming software directly to where the machine operates. Let's talk about that now. Let's start with Ethernet type changes. This is a very common thing that you can change right after a machine has been deployed. So let's say the IT department does a kind of reformatting or upgrade of the factory network and your machine is sitting on your customer's factory network. Well, they would like to be able to modify the IP address, net mask, and those sort of Ethernet type parameters without making a configuration change. So as changes are made over time in your original program, you could utilize those variables to create some custom screens, or maybe a custom screen on a SCADA package or HMI that would allow these IP addresses and those sort of Ethernet parameters to be changed. But there is another scenario that also can occur, and that is at some point after you have deployed your machine, your customer needs to swap out a sensor. A sensor has failed, it needs to be swapped out, and maybe the original sensor was 4 to 20 milliamps, and the new sensor, they cannot find one of those in stock. There is the same sensor but with 0 to 10 volt output on it instead. So it would be nice to be able to support that sensor without having to reprogram the controller So could that be done? Well, in the case of the CPU250, we have given you the capability of modifying some of your parameters, such as sensor ranges, on the fly. How do you do that? Well, let's take a look. So what we have on the screen here is a table that shows what changes can be made through variables to flexible inputs. Now there are 8 flexible inputs on the CPU 250, inputs 9 through 16, and each flexible input has 4 configuration words that allow you to adjust its functionality. So that table on the right there shows 4 words, and that is 4 words for each of the 8 channels. And the type of things you can adjust are, first of all, is that input used for digital purposes or as an analog input? If it is selected as a digital input, what is the voltage range? 24, 12, 5 or custom? If it is custom, what is the threshold between 5 and 20 volts? What is the off threshold between 5 and 20 volts? So if you're using a flexible input as a digital, that is what you can adjust based on that third column in the chart on the right. And if you are using a flexible input for analog purposes, you can select the range. It is in 0 to 10 volts, 0 to 20 milliamps, or 4 to 20 milliamps. And then once you have selected the signal type, how do you want the data to be scaled? Do you want to take advantage of all the bits in the analog input word and just have 0 to 32,000 from min to max? Or would you like something mathematically simpler, like 0 to 1000 for the scaling where 0 is minimum and 1000 is maximum? That gives you a simple 0.1% resolution, and in some cases can make scaling math very easy. So that all comes down to your preference. But that could be changed on the fly as well. Now the most common thing that would be changed would be the signal type of the sensor, whether it is analog or digital. Now as we mentioned, we have 4 words for each flexible input. For configuring these things, we have talked about so far, for all the channels that are used as analog, there is a separate configuration word, just 1 word, total for all the channels that are analog, for adjusting the filtering. So 0 at minimum filtering, 7 at maximum filtering, and it can be in between to balance responsiveness versus signal stability. And then for all channels that are being used as digital, you have got a single word to configure between positive logic and negative logic. Now 95% of the time, or maybe even more than that, you're going to be using positive logic. But if you do use negative, it is available, but you do not have the option of the custom threshold anymore. So that is what you can do on the flexible input side. Now just one more mention on how you would deploy this. So for each of our 8 channels, if we are using register-based programming, you would assign 4 consecutive R-type registers to hold this configuration information. If you are talking about variable-based programming, which we have been encouraging for some time, then you are talking about an array-type variable of the word type with a dimension of 4. One of those variables for each of the 8 channels. So that is how you would deploy that. And you would just need one simple variable for analog filtering, another simple variable for the digital input mode. Now on the analog output side, you can configure signal type, data range, and what is called halt stage. What happens to the analog output signal when the controller goes into stop mode? Does it continue sending out the value that was there before the controller went into stop mode? That is called hold value. Does it go to minimum, which is usually 0 volts or 4 milliamps or 0 milliamps? So you can adjust that as well. Now this is not as useful as making changes on the analog input side. Why is that? Well, because the analog outputs are already segregated by signal type. So the first four analog outputs are milliamp type, and the next four outputs are voltage type. So if you are going to be using a voltage sensor instead of a milliamp sensor, you would have to change channel locations where you wired the sensor. So this is not as useful in terms of changing on the fly as on the input side, but the capability is there as well. And you can see you have got 3 words of configuration per analog output. So that means 3 consecutive registers per analog output if you are using register programming, or 1 word type array with a dimension of 3 for each analog output channel if you are talking about analog output configuration. For our demonstration, we are going to start by being in Cscape 10.2, and let's go ahead and take a look at our demo. Now before we start with the Cscape side of things, let's take a look at what we have going on in the bench for the demonstration. So you will notice there is our CPU250, but you will also notice we have got another Horner product here, and that is because the CPU250 does not have a built-in screen. So if you are going to manipulate the hardware configuration of the CPU configuration from registers or variables, then you are going to need some way of doing that. And one of the ways you could do that is with a remote screen, whether it is an HMI screen or whether it is a SCADA screen from a controlled room or something similar. And remember, we are not going to be making I/O configuration changes very frequently, so it does not necessarily have to be something that you access all the time. But to stimulate that remote screen or remote SCADA screen, we have used the Micro X7, and we are just using it as a HMI right now. And we have it talking to the CPU250 over Modbus TCP using what we call native addressing, so that the micro and the CPU can talk to each other using Horner nomenclature. You do not have to do any conversion to Modbus register types or anything like that, but the whole purpose of this demonstration is to show you how we can manipulate the I/O configuration from a remote screen without pulling out Cscape. So that is what we have going on the bench. Let's take a quick look at Cscape now to see what programming is required. Now we are starting in this program that is residing in the CPU250. Let's start in the hardware configuration. Now we will go to the local I/O tab. Now there is no configuration on the fly for digital inputs, nor for digital outputs, so we are not doing anything there. But on the flexible input side, as we showed on the slides, we do have the ability to assign variables here, and for each flexible input channel, we can assign a variable that is a word type variable, an array word type variable with a dimension of 4, and again, we have one of those array variables for each of the 8 flexible input channels. Now, in addition to that, we have got a single word variable for the filter for the analog channels and a single word variable for the positive or negative logic selection for all the digital channels. So those are the variables we have assigned for flexible inputs. Now on the analog output side, we also have the ability to assign word array type variables, this time with a dimension of 3 for the 8 different analog channels that we have here. So that is all that is required there. Now where are these variables being manipulated? Well, they are being manipulated by the remote screen that we showed you on our bench for Modbus TCP. So we have to set up Modbus TCP. In this case, we are just using the CPU250 as a server. So we have just checked that checkbox and made sure we have an IP addresses, a net mask, and gateway configured. Now in a real application, we would assign variables to these as well, but we have just hard coded it here for demonstration purposes. And then there is one final step, and that is this. Because the data to manipulate those variables or to fill those variables is coming in over the network, we had to do some variable mapping or some register mapping to those configuration variables. So here are those configuration variables. Here are the word arrays for the flexible inputs. Here are the word arrays for the analog outputs. And then here are the symbol variables for the filtering and for the positive and negative selection. And for each of these, we have assigned a starting register for these. Why do we have to do that? Well, because the data is coming in over a network, they have to be at a known memory location. So what we have done for all this configuration data, as an aggregate, we have 58 registers assigned here, starting at register 1001 and going through 1058, because remember 56, and there are 2 additional ones after that, 5758. So that is what we have going on here. So there is no other programming required in the CPU250. All the manipulation is being done elsewhere. Now let's go to the hardware configuration for the Micro X7, and now let's look at LAN 1. This time we are not a server, this time we are a client. So the Micro X7 is the Modbus TCP client, and it is scanning those registers that we talked about where the configuration data is mapped. This also happens to be scanning the standard I/O data as well, although that is not a requirement. That is just what we have added to our Modbus map here. But again, you do not have to do this Modbus part to make this work. You just have to have some way of manipulating those variables in the CPU250 that is controlling the I/O configuration. And then we have some logic here for controlling things like visibility on the 2 screens that we have created. So this is a screen that contains all the flexible input data, and we have the ability to manipulate that with the simple toggle switches for digital and analog. Some text tables for selecting through the different available ranges for digital and analog types. And then of course, we also have text tables for the different available data ranges as well. And these will either be displayed or not displayed, depending on whether the channel is configured for digital or analog, depending on the voltage threshold, if it is digital, or depending on the signal type, if it is analog. Let's take a look at what it looks like on the bench. So for this configuration, what we have is for the first 4 analog channels, we have set those for analog. This is a toggle switch that toggles between analog and digital. The first 4 flexible channels we have set for analog. The first 2 we have a type of 4 to 20 milliamps, and the second 2 we have a type of 0 to 10 volts. And because for demonstration purposes, we also set the data range or the scaling differently for the current channels, as we did for the voltage channels. Then the final 4 flexible inputs we have set for digital, the first 3 being 24 volts and the last one being set for a custom on and off threshold. And right now it is set for an on at 20 volts and an off at 10 volts. And then over here we have a variable power supply. So right now if we take a look at I16, which is the last of the flexible inputs, that LED is off. Until we get to 20 volts, that LED is going to stay off. Once we get up to 20, then you will see it turn on. And it has turned on, and then once we get back down to 10, you will see it turn off again. Got to go further down to 10, and you can see it is off. We are down around 7 volts now. Now let's adjust the range, and let's say we want to adjust the threshold for on to be to 18 volts instead of 20. So now as soon as we get to 18, we should see it turn on, and we did. And then again, we have to get down below 10 before it turns off again. So as you can see, we can very easily manipulate any of these parameters through those configuration variables that we assigned. And then if we move over here to the analog output side, you can see we have got similar things happening here as well. So we have set the first 4 channels for 4 to 20 milliamps. The next 4 are 0 to 10 volts. We have manipulated our scaling a bit, or our data range there. We have set our stop value to be minimum for all the analog channels, but we could change these on the fly if we had a need to. Again, as we mentioned earlier, having the ability to change analog input settings is more valuable than analog output settings because you run into that scenario much more frequently. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so we are on again next week with the CPU and OCS I/O CAN wiring. So if you'd like to register for that, then that registration link is up. Other than that, there's no questions in, so we can leave it there. Thank you again, and we'll see you next time.